Alright, people, as promised, I will deliver you some optimization problems. Um, these are designed for those of us who are feeling like this lady in the picture right here. It's been a while since I've made one, so if I'm a little rusty, sorry. But let's go ahead and get started. Let's go. If I paste the first problem in here, this is problem number 29, so I'm going to have to go and cover our friend here for a little bit. Number 29 says that a cylindrical can open at the top is to hold 500 centimeters cubed of liquid. That tells us some really important information right off the bat. So if I'm going to use any kind of information, I'm going to use that. And so the information given is going to be that the volume is equal to pi r squared h, because we're dealing with a can. And we know specifically that the volume is 500. So that's going to equal pi r squared h. Now it's asking us to find the height and radius that will minimize the amount of material needed to manufacture the can. So basically what I'm being asked to do is to optimize the dimensions of the can specifically to the height and radius, and specifically looking for a minimum. So what I need is I need a formula that will allow me to connect radius and height when it comes to things that are wrapped around a can. So I believe that is the surface area of a can, which is equal to the area of the base plus 2 pi r h. Now, in case you guys don't remember the surface area for a cylinder, it's typically 2 pi r squared h, but the fact that the can is open at the top means I only have one base. And then 2 pi r is the circumference, and then the h stands for height. So again, I used 1 pi r squared because this can is open at the top. So the problem with this is that if I try to derive this formula, I end up with some product rule and some multiple variables. We don't want that since we're in single variable calculus. So I'm going to use my volume formula to reposition some things. I'm going to go ahead and solve everything for r, or at least I'm going to derive everything for r, so I need to solve everything for h here. So hopefully it makes sense that h is equal to 500 over pi r squared. Now this gives us a couple of pieces of information as well, because we need to find our domain restrictions of the height. The domain restrictions of the height are going to be 0 to infinity, with open brackets, because you can't put a 0 in here, otherwise you'll end up with some kind of crazy asymptote. And then infinity, because this radius can actually get really, really big. The height will approach 0, but it won't get there. So obviously we won't be including these, but it's good to just know what the boundary is. So I'm going to take the height and reposition it into the height of this formula here. So I get surface area is equal to pi r squared plus 2 pi r times 500 over pi r squared. So now that everything's in terms of r, I can go ahead and cancel a couple of things. The pi and r are going to cancel with the pi and r squared here, leaving me with an r on the bottom. So my formula is going to be s is equal to pi r squared plus, I'm going to multiply this in, and I'm going to get 1,000, 1,000, and technically I have an r on the bottom, but for derivative purposes, I'll go ahead and make it r to the negative 1, and that's a 2, just to be clear. Okay, so I think we are ready to derive this thing. So if I take the derivative of the surface area with respect to the radius, what I get is, since pi is a constant, I get 2 pi r minus 1,000 r to the negative 2 power. From here, I need to find a critical number in all of this, so I'm going to go ahead and factor out a 2. And that's going to also factor out an r to the negative 2. Now what that leaves me on the inside is with a pi r cubed minus 500. And what that tells me is that my critical number is going to be produced by 500 over pi, and that's the cube root of that value. This expression here is always going to be positive, This expression here is a cubic function, which is negative on the left, positive on the right. So I know I've got a local minimum here, and actually an absolute minimum for this particular problem. So from here, I can say that when r is equal to the cube root of 500 over pi, the materials, oops, running out of space here, materials will be minimized. Now, I understand I forgot h. That is why I left myself some space right here. So when r is equal to this and h is equal to, well, let's find out. I need to find a really easy and safe method to plug in r. So I'm going to go ahead and choose this function right here to plug in r. And for time purposes' sake, I will tell you right now that I got 500 over pi times pi over 500, and that's being raised to the 2/3 power. Now, the back of the book got something different. They got a really, really simplified version. I believe it was the cube root of pi over 500 or something like that, or the cube root of 500 over pi. That's after doing some really painful algebra. I will go ahead and leave it right there for the sake of time. So there is your first problem, number 29. I don't believe it's particularly difficult, but go ahead and rewind or hit the pause button if you feel like you need to. Let me upload the next problem. So in problem 39, we are being asked to optimize, it looks like, the area of this trapezoidal figure right here, because we're trying to drain some water through it. Now, in order to optimize the area of this trapezoid, they're encouraging us to use this angle theta right here, which is actually a really good idea. I would say in this problem here, the hardest part is actually not even the calculus at all. It's everything that leads up to the calculus. So hopefully you can follow along and it'll make sense. So hopefully you can follow this much, that if this side of the trapezoid is 5 feet, that means that this side is also 5 feet. And then if we've got a distance going down to here like this, that means that that same distance is occurring right here. So I've really got this right triangle happening. And that this angle here, whatever height I find for my left side of this triangle, this side, will be equivalent for this side as well. And this 5 does not apply to the height. So let me fix that actually. Get rid of u. The 5 actually applies to the hypotenuse of that triangle. Okay, so if theta is this angle here, what I can say is that the bottom side of this triangle is going to be, let's call it x. And let's call this top side y right here, this leg. So if I look at it from the angle's perspective, now it's a little bit misleading, so I'm going to go and move theta right here. Okay, so theta is this inner angle right here. I'm going to go and just eliminate u because u could be confusing. That was not helpful. Okay. Cool. So now I need to solve for x. Well, if I look at x, then I'm looking at the relationship between this angle, the x, and the 5. That's the only relationship that I can really think of. Well, the relationship between an angle and an adjacent side and an opposite and a hypotenuse side is cosine. So I can say that cosine of theta is equal to x over 5. And then the same thing here, I can say that because this right part of the triangle is y, this left part of the angle is also y, so I can say that the opposite and hypotenuse is going to be sine of that angle is equal to y over 5 again. This leads me to say that x is equal to 5 cosine. 5 cosine theta, and y is equal to 5 sine theta. Now, why did I put myself through all of that anguish? Because in order to find the area of a trapezoid, I have to revert to this formula right here. The area of a trapezoid is equal to 1/2 times the first base plus the second base, and that's times the height. So, who says geometry is a terminal course? So, what I have found right here, this y is the height. And then this 5 cosine theta is going to play a role in helping me find the base. So let's find out the measurement of the base. So hopefully it makes sense that this top side here is 5 cosine theta, which means that this side is also 5 cosine theta. And if this bottom piece is 5 feet, then this top piece is also 5 feet. So what I have found is that the base of this thing is equal to this. It's equal to 5, which is this piece, plus 5 cosine theta and another 5 cosine theta. That gives me 10 cosine theta. So I believe we have enough information at this point to write the equation of the area of the trapezoid. So A is going to equal 1/2 base 1 plus base 2. So that would be base 1 is 5, and then plus base 2 is plus 5 plus 10 cosine theta times the height, 5 sine theta. So if I simplify all of this out, what I'm going to get is I'm going to get 1/2 times 10 plus 10 cosine theta times 5 sine theta. Now, a couple things can happen here. I can simplify some stuff out. If I factored out a 10, I would get 10 over 2, so I would get 5 times 1 plus cosine theta times 5 sine theta. The 5 and this 5 are going to multiply out to become 25, and I just have this sine theta here. Or it could have been on the other side. Let me see if I can't clean this up one last time. That is a cos. So let's go ahead, and we have no choice. We have to product rule at some point, whether I distribute or not. So let's go ahead and product rule now. I get the first unchanged times the second one's derivative. So this is 0, this is negative sine theta, plus the second unchanged times the derivative of the first. So let's go ahead and clean this up here. Whoa, I'm running out of space here. So this is dA over d theta. Once I clean it all up, I'm going to get negative 25 sine squared theta plus 25 cosine squared theta plus 25 cosine theta. So now that I've taken the derivative, hopefully it makes sense that eventually we're going to solve for something. Now, we've done a lot of math so far, but keep your eye on the prize. We are eventually going to set our derivative equal to 0 so that we can find out where this thing maxes out, because we're trying to optimize the area of the trapezoid for a maximum. So, because I'm going to end up solving for this, and I've got sines and cosines everywhere, the dominant term here is cosine, so I'm going to go ahead and convert sine into some kind of thing that involves cosine. So I'm going to use a good old friend of ours, a trig identity. And that's going to equal negative 25 times 1 minus cosine squared theta plus 25 cosine squared theta, and then plus 25 cosine theta. So from here, I can go ahead and set this equal to 0, or I can go ahead and just kind of mess with it a little more. I would get negative 25 plus 25 cosine squared theta. Junctioned onto this thing, I would actually get 50. So I'll go ahead and fix that right now. We'll go and skip a couple. This is a 50 cosine theta, so that's goodbye to both of you. And then plus 25 cosine of theta. Now that's going to get set equal to 0, so let's go ahead and do that. 50 cosine squared theta plus 25 cosine of theta minus 25 equals 0. I can divide out a 25 here, so I would get 2 cosine squared theta plus cosine theta minus 1 equals 0. I can go ahead and factor that out. And I'm going to get 2 cosine theta minus 1. And I'm going to get cosine theta minus 1 again. So cosine of theta is going to equal 1/2 or 1, which means that theta equals, now, we are only operating, it says, between 0 and pi over 2. It says it right here. So the angles between 0 and pi over 2 that produce these answers is only pi over 3. So from here, you want to find out how this thing is going to be optimized. So give me a second. Let me erase this stuff here. So from here, we are going to figure out the area when all of this is happening. So the area of various thetas, theta was at 1.0, given our boundary that was given to us in the problem. The area when theta was pi over 3, which we found, and then the area when theta was pi over 2, which they gave us within the boundary. So I need a safe place to plug this into. I'm going to go ahead and use something that I deleted, which is, if you look back at the sine, 25 sine of theta times 1 plus cosine of theta. So see if you can't find that on your paper. For a of 0, I get 0. For a of pi over 2, I get 25. And then for a of pi over 3, I get 75 root 3 over 4. Again, I just plug things in into a convenient formula that will allow me to figure out what the area of the trapezoid would be. Obviously, this is your largest area. So your statement could be the area is maximized or maxed when theta equals pi over 3. And that's it for this problem. Alright, let me upload the next one. So before we begin this problem right here, I do need to let you guys know of a function that you guys should be familiar with, and it's actually pretty common sense. If I was to ask you guys how would you make profit, your answer should definitely not be to hold a new teacher shower. It should actually be to figure out a function that would allow you to make some money. We can say that profit, let's say if I had just some function p of x for p for profit, that should equal something that, a term in econ that's used to, or business that's used to discuss how much money you make, is a term called revenue. And so the revenue function, right, is how much money you intake, and then you should subtract the cost that it took to earn that revenue. So profit is going to equal the revenue made minus the costs incurred. So hopefully you want to try to minimize the c of x as much as possible, and I believe that is what we are going to have to try to do in this particular problem. So it says a chemical manufacturer sells sulfuric acid in bulk at a price of $100 per unit. So what that means, this statement right here says that if they sell the sulfuric acid at $100 per unit, that means that their revenue is going to be $100 for every unit that they sell, and that's going to be their profit. Now, the cost that they incur is this ugly thing right here, and they give that to you. So that's minus 100,000 plus, I'm going to have to unfortunately go to 2 or even 3 lines here, and don't worry, I will eventually clean this up, plus 0.0025x squared. Now don't forget, that's being subtracted, the whole thing is being subtracted, so when I go to clean this up on the bottom here, I'm going to distribute in that negative. So what I get is p of x ultimately equals 100x, or I'm sorry, negative 100,000, this is after everything's been simplified, plus 50x minus 0.0025x squared. Okay, so they also tell us a couple of things about this function that I will get into in just a second. If we look up here, it says the daily production capacity is at most 7,000 units. So if we look at the boundaries of this problem, this company here could produce nothing, or it says they can produce at most 7,000 units of this sulfuric acid. So we are bound by this domain right here. So it looks like we just need to figure out how much we need to sell to maximize our profit. So we need to take the derivative and then find out our local max, or our absolute max. In this case, this thing is going to be killed off on derivative. We get 50 minus 0.25 is going times 2 is going to be 0.0050x. Now, your critical number here that is going to allow this thing to zero out is actually 10,000. It's a upside down line, so it's going to go plus minus. Here's the problem. You found 10,000 as your critical number. However, you're bound by 7,000. So what that means is that 10,000 is outside of your domain. So all you can do in this problem is test the numbers that they gave to you, because the number that you found is outside of the domain that you have been asking found. So if you plug in p of 0 into this original function here, you will get negative 100,000, which means, well, I'm not going to say anything yet. P of 10,000 is going to get you a big number, but P of 7,000 is going to get you 127,500. And that is because, again, your production limit is 7,000 units. Okay, that is, I believe, part A. Part B says, would it benefit the manufacturer to expand the daily production capacity? Well, you know what, for that, let's see what would happen if we actually plugged 10,000 in our critical number. Our critical number, if we plugged it in, we would have earned $150,000. That's pretty good. I think that's a lot of money. I would like to earn the difference between those two. I'd like to earn any of those salaries, actually. That'd be kind of cool. But anyway, part B is yes. They should raise their production. Actually, not even should. They must. They must raise their production. It is necessary. Okay, the part C here talks about something called marginal profit. Now, if you look in the book, marginal profit is used to determine how much money they're making per unit. So that's why they specifically ask, the effect on the profit if they increase production from 7,000 to 7,001. What we're basically doing is we're finding out how much money they would make per unit past 7,000. So we know that P of 7,000 is equal to 127,500. So 127,500 is going to be the amount subtracted. And that we're going to subtract that value from P of 7,001. And so P of 7,001 is equal to, and I'll go and let you plug that into the original equation, that is equal to 127,515 minus this value. That's going to get you an extra $15 per unit of sulfuric acid. So they earn an extra $15 per unit past 7,000. They should definitely produce more, although it was not as climactic as I thought it would be. So that is number 43. It is a profit problem. We will do another one in just a second. Hold on for a second. Number 44 is next. A firm determines that X units of its product can be, I think that's supposed to say, this is supposed to say sold, but there's a hole puncher there, sold daily at P dollars per unit where this is true. The cost of producing the units per day is this value here. So we should know, and actually this problem is really cool because they're guiding us through. They want us to find the revenue function and the profit function. Well, if we look at this problem, I'm going to write this in catch up actually. If we look at this problem right here, X is equal to 1,000 minus P. Well, P is the dollars per unit that's earned. And so if we wanted to look at how much dollars per unit was actually earned, because the X is actually the units, we want to figure out what P is. So what I'm going to do is I'm going to flip-flop the P and the X, and that means that I earn P dollars for every 1,000 minus X, whatever this value produces, because X is the number of units that's sold. So that's how many dollars I'm going to earn, this P right here. What this tells me is the revenue. Now, if you look at the book, the book dictates that revenue is equal to the number of units per dollar sold. So what they say is that R of X is equal to P times X. So I use that information to say that R of X, which is this revenue function right here, R of X is equal to, now if P equals this function here, then R of X is going to be X times 1,000 minus X. Or I can simplify that into 1,000 X minus X squared. The profit function is simple. Profit is equal to the revenue minus the cost. So that's going to equals revenue, which is 1,000x minus x squared minus 3,000 plus 20x. Now that's going to simplify out into 1,000x minus x squared minus 3,000 minus 20x. Now, I can go ahead and simplify everything here. I'm going to keep writing on this black part of the screen. It eventually simplifies out into negative 3,000 plus 980x minus x squared. Okay, so again, this is my profit function. You guys notice that it's parabolic. It's specifically an upside down parabola. So one thing that we should kind of expect out of this is that if it looks like this, there's going to be a peak at which we maximize our profits, and then we're going to start seeing our profits go down, and we'll talk about that maybe. So get rid of you. Okay, so we just solved A and B so far. Now it says assuming that the production company is at most 500 units per day. Determine how many units they must produce to maximize their profit. So what they just gave us here in C is the boundary that we're going to use. So I'm going to write C down here actually. We could produce at most zero. At least zero. For our lower bound, and we can produce at most 500 units. So we have to find a critical number here because these are just our bounds. So what I'm going to do is I'm going to take the derivative of this function. So I know that P prime of x is equal to 980 minus 2x. My critical number here is going to be 490. It is an upside down line, so I've got a positive here and a negative here. Luckily, this is a max. Okay, cool. So we are going to go ahead and figure out what our profits are if we produced nothing, if we produced 490 units, and if we produced 500 units. Well, if we produce nothing, then believe it or not, we're not going to be producing nothing. We're actually going to be in the hole, $3,000. If we produce 490 units, then we are going to earn $237,100. And strangely enough, if you figure if we produced more, then we would earn more, right? But it turns out that if we produce 500 units, we earn 237,000 flat. And again, I got these numbers just by plugging them back into the original function. Now, I'm going to offer a bonus point for anybody who decides to do this. If you can come in on Monday and write maybe a couple of sentences as to why this might be true, if I buy it, I will give you an extra bonus point. But we can talk about that when we get to Monday. Cool. I think we just found D also. We just found the maximum profit. So that's D. Thank you. Good job. And then what price per unit must be charged to obtain the maximum profit? Okay. Well, we have to go back. We have to go back to our price function here. This is this thing here. And so if X is if our maximum profits, right? Our max profit is $237,100 when X is equal to 490 units, then we have to figure out the price per unit. Well, we can go to the price function here and say 1,000 minus 490. So to solve for E, we would say that P is equal to 1,000 minus 490, which is $510 per unit. Good profit. Okay, let's go ahead and move on to the next profit problem. Number 45 is kind of a holy guacamole kind of problem, and it's not something that's completely intuitive, but once you see how it's done, it hopefully makes a little bit of sense. At least it did to me. A certain chemical manufacturing process, the daily weight, Y, of defective chemical output depends on the total weight, X, of all output according to the empirical formula that, where X and Y are in pounds. If the profit is $100 per pound, actually, before we even read on, let me establish a couple things. What this sentence is saying here, this really difficult to understand sentence, they're saying that Y is all of the defective chemical. And then what they're saying is that X, not the function, but X is the good chemical. So what we get is the output of the defective chemicals is dependent upon this formula. Okay, so we want to figure out if the profit is $100 per pound of non-defective chemical produced and the loss is $20 per pound of defective chemical produced, we need to figure out how many pounds of chemical should be produced to maximize the profit. Well, at its core, this problem is exactly the same. We know that profit is going to equal revenue minus cost. Okay, the trick is to figure out which one is which. Well, revenue is produced by non-defective chemicals. If X is the good chemical and Y is the defective chemical, then hopefully it makes sense. And here's the thing that you have to understand also, is that producing defective chemicals is unavoidable in this problem, but you're going to produce good ones too. So hopefully it makes sense that the revenue produced is going to be the number of good chemicals produced minus the number of bad chemicals produced. Think about that for a second. If you have to, hit the pause button. And we earn $100 per every pound of that happening. Now the loss is just $20 for every pound of defective material, so $20 for every bad one. And that's going to be our profit. Now, once you have this in mind, deriving this thing is a piece of cake, because you're going to get 100x minus 100y minus 20y, and then you can go ahead and simplify that even further to say that your profit is equal to 100x minus 120y. Now, if we go to derive this thing, it looks clean, but we still have this pesky y to deal with. We're not in multivariable calculus yet. It's a good thing they gave us the output formula for the defective chemicals, which is this guy. We punch that into the y function here, and then we take the derivative of it. So p of x is equal to 100x minus 120 times 0.01x plus 0.40, 3 zeros, 1, 2, 3, and a 3x squared. I will let you go ahead and distribute and algebra that stuff out. Hit the pause button and please do it, because I'm going to jump straight into the derivative for time's sake. The derivative is 98.8 minus 0.0072x. Now, a couple of things. When you found the profit function, I need to let you guys know a couple things. Notice the profit function is a parabola, specifically an upside down parabola. So when we talk about boundaries, if they don't establish any, and we're trying to maximize the profit, there is no need to find any boundaries on our own, because if we're just trying to maximize this thing, there is only going to be one maximum here, and it's going to be at the vertex. So in this particular problem, it is not necessary to find your boundaries, because the function that you found that'll maximize your profit is going to be an upside down parabola. So you're only going to have one max. And that max, and even if you did have boundaries, those boundaries are going to be below your max anyway. So, no need to test endpoints. Whatever max you find is going to be the absolute max. Based on that, I'm going to do something that a lot of you guys didn't do on the final, but it's okay. I'm going to take the second derivative of this thing. P double prime of x is going to be negative 0.0072. And because my second derivative is negative, I know this is concave down, and therefore a max. I do need to verify that on the AP test in order to get credit. If you don't want to, it's okay. You can use the number line analysis chart to do that. If you're particularly feeling sign charty, go ahead and do so. So, what we need to do is we need to solve for x at this point. So set this thing equal to 0. And you will find that 90, oh, that's an ugly 8. 98.8 is equal to 0.0072x. And x is going to equal 13722.222 pounds. Which means that when 13,722.222 pounds of chemical is produced, profits are maximized. Okay, cool. Let's keep moving. Actually, when I said let's do the next one, that was actually just a joke. I think you guys are optimized out for the day. I'll upload the second set of them when we get back, and then we will continue our quest in optimization then. See ya.